So, first thing, in order to do anything to our DNA molecule, we need to take it apart. And we're not going to take it apart the way that helicase takes it apart, but rather we're going to use an enzyme that is going to cut up the DNA. And these are called restriction enzymes. And so they act as sort of molecular scissors. We find them only in bacteria. Bacteria have these restriction enzymes as a way to protect themselves against viral DNA that is injected into them. They cut up the DNA before it can do any sort of damage. No eukaryotic organisms have these, so very unique to bacteria. What happens is certain enzymes recognize certain sequences of DNA, and when they see those certain sequences, they will break the bonds between them, both the peptide bonds and also, I'm sorry, not peptide, the phosphodiester bonds between adjacent bases, and then also the hydrogen bonds between base pairs across from one another. And wherever this cut happens is called a restriction site. So what are we going to do with this? Well, basically, each enzyme, each restriction enzyme, has a different recognition sequence or a restriction site that it's going to realize. So if you look at this page in restriction 1, when we take the same piece of DNA as in the first picture and the second picture, you'll see that because we use restriction enzyme 1, it cut the DNA at 3 different spaces. They all had that restriction site. And this created 4 fragments. Whereas with restriction enzyme 2, it's going to cut it at 6 different places, and that results in 7 fragments. So the important thing to remember here is that when restriction enzymes cut, they can be found, their restriction sequences can be found in multiple areas on a gene sequence, and they will cut every time that that recognition sequence is recognized. And in addition to that, each restriction enzyme recognizes a different restriction site or recognition sequence. So what can we do with this? We cut up our DNA into a bunch of different fragments. Well, what if we separate those fragments and we separate them and sort them based on their length or their size? So this is going to be the first technique here. I want to draw your attention to it. Okay, here's terminology, right? Vocab term, gel electrophoresis. That is our first concept here. Gel electrophoresis is a biotechnique that is used to separate DNA fragments by size. So obviously, in order to get fragments, the first thing we have to do is cut them up with different restriction enzymes. Different enzymes will produce different patterns and different sizes of fragments. Now we have all these fragments, in this pile. How do we separate them? We're going to have to use another property of DNA. So if you look here, I'm just going to do a quick little drawing. Okay, there's your phosphate group, here's your sugar, and then you have your base, right? Like let's say that's purine, okay? The phosphate group is a PO4, and it is a 3- when it's not attached to anything, but it's bonded here. Anyway, what I want you to focus on is the fact that that phosphate group has a negative charge. And now think about the fact that every nucleotide of the entire DNA sequence has that negative charge. And so that gives DNA a negative charge. Okay, that's really important because this is how gel electrophoresis works. So we're going to place the DNA into a gel that's represented by the black box here. This gel has the same consistency as Jell-O. So is it solid? No. Is it liquid? No. It's in between. And that means it's porous. And so what happens is these, micro tiny pieces of DNA are going to be able to work their way through the gel. And you can see we have motion here, that the DNA fragments are going to start at the top where they get loaded, and they're going to move through the gel in this direction. What's going to cause them to move? We supply an electric current. Oops, sorry, that wasn't a very good circle. Oh, okay, it's going slow. Anyway, we supply an electric current. Oops, I'm sorry. Nope. All right, so there's an electric current here, and we put a positive electrode at this end and a negative electrode at this end. So if your DNA that you're putting in is negatively charged, right, that's a symbol for a negative charge, it's going to be drawn through the gel and attracted to the positive charge that's down here. So that's what gets those DNA fragments to move through the gel. Okay, this is just a side view of what this technique looks like. It happens in a little plastic box, and I can show you what it looks like in class. Here's the result. Okay, so taking a look here, just going back to the first step, we have our DNA sample. We're going to cut it up with restriction enzymes, so we have fragments, and then we're going to place those fragments into the one end of the gel, and we're going to attach electrodes to either side. So you'll see negative over here, and then the positive is going to be over here. That way, what's going to happen is our DNA is going to move down the gel towards the positive end. So how does this separate them based on size? Here's the key. Smaller fragments move faster and therefore travel farther than larger fragments. Okay, so here is the result of a gel. Okay, this is what it looks like. This is an actual picture of a gel. It's stained blue because we add a dye to it so that we can see it. Normally it's clear, but if we want the clear DNA to show up against the clear gel background, it's going to turn blue. So all of these little, they sort of look like a little handlebar here. These are all fragments of DNA. And in each lane, right, if we read this going vertical here, okay, each lane contains different fragments. Some of them are the same and some of them are different. So we can use this as a way to compare. When we look at these little pieces here, we call these bands, okay? They're the banding pattern that shows where each of the fragments are. So the ones up here are really large. Let's say it's like 20,000 base pairs, so 20 kilo base pairs. So that means that DNA sequence is 20,000 base pairs long, whereas the ones down here, they may be only, 8,000 base pairs. So now, if we know the size and the number of fragments in a sample, we can then compare that to unknowns and use that to estimate the sizes of fragments. Or what this picture is trying to show is we can use it to look at how we compare. Before I move on, I just want to make sure, big star next to the 4 descriptions here, 1, 2, 3, 4, you may have to describe in an essay the 4 key steps of gel electrophoresis, and this is what I would focus on. So how do we use this? Well, all right, what we do is we have our gel, right, and here are our banding patterns. So we see we've cut the DNA up into 4 fragments. The closer to the top, the larger the fragment, represented here by the larger size rectangle. And then what we can do is we can look at this and figure out, oh, okay, well, this is where we had these cut patterns made, and we can determine the size of the fragments. We can't determine anything about the sequence from this technique. That is going to be another technique known as DNA sequencing. But still, this is really useful. For example, if we're studying mutations. Let me go back a screen here. Okay, looking down here at this, remember how I said we could compare this, this lane of data to another lane of data and look for differences? All right, well, what this might be showing here is that in the normal sequence, there are 1, 2, 3 bands that are produced. So in a linear piece of DNA, that means that our restriction enzyme cut twice. But let's say there was a mutation that occurred and it changed the sequence in one of those recognition sequences. So now the enzyme doesn't recognize that cut site anymore up here, and instead we only get 2 fragments. So that shows where a mutation has occurred, and we can use this sometimes to track changes relating to disease. So for example, this might be the pattern that your CFTR gene, let's say, that's for cystic fibrosis. This is the gene that is the normal function, and then this one shows what it would look like if it were mutated. So if these are my known fragments, and then, let's say this is individual 1, individual 2, and individual 3 from a family, we would say, well, no one in the family has the mutation for cystic fibrosis, but, person number 2 here has a mutation that is different from the normal. It might not be cystic fibrosis, it might be something else. So we can use that to compare sequences and, make predictions about mutations.